His research is focused on cosmology and how cosmology can be used to inform us about fundamental physics. And today he will be telling us about signatures of the early universe from BAO.
Thanks a lot, Tom. Thanks a lot for inviting me. It's great to be here at CITA and discussing with all of you. And so indeed, today I want to tell you something about work that I've done with this kind of great group of people here over the last few years on extracting data, or extracting information on the early universe from some specific large-scale structure observables. But before we go there, let's look at our universe. I really like this kind of depiction, in particular for kind of purposes of kind of this talk, or introducing this talk, because it shows kind of some of the important kind of slices or snapshots of the universe that are important for cosmologists, in particular an early universe cosmologist. Because kind of back here, we have kind of about today, and then going back, essentially we have the observable universe. In particular, of course, with kind of the large-scale structure of the universe, and meaning in particular kind of the distribution of galaxies that we can measure with galaxy surveys. And then going back further in time, we of course have the large scattering surface and the kind of the cosmic microwave background that we are very successfully kind of probing these days. But then, if you want to test the universe at earlier times, or times earlier than about 400,000 years, we can't really test it directly. One small caveat to that might be kind of gravitational waves, but kind of electromagnetically, we can see back to the last scattering surface, and then we're done. And so we need kind of if we want to test the universe at earlier times, we need there to be something left over. And so we've very successfully done that with Big Bang nucleosynthesis, which gives us a snapshot at about 3 minutes after the Big Bang. And so we can do calculations, and they agree very well with the light element abundances that we can extract in the late universe. But so more generally, you can ask the question, well, what can we learn about the early universe and from the early universe? In particular, is the early universe following kind of the standard evolution that we think by combining kind of lambda CDM cosmology with, or kind of the cosmological model with the standard model of particle physics, or might there be some kind of deviation? And then also, if you kind of even go beyond the hot Big Bang into the very early universe, the Primal Universe, we can ask, well, was there something like an inflationary epoch, or was there maybe something else, or was there anything, or whatever? And so in this talk, I will kind of touch on all these three bits by kind of looking at a specific observable that I'll be introducing in a few minutes, in order to test both kind of some important properties of neutrinos in the early universe, and then also as a probe, so using this observable as a probe for some generic important models of inflation that go beyond the standard single field slow roll paradigm. And of course, feel free to interrupt at any time and ask questions. OK. So let's ease our way into kind of the observable part and ask the question, well, so the CMB is awesome. We've been able to learn a lot about the CMB. It's pretty easy, quote unquote. So why should we consider kind of this additional slice of observations with the large-scale structure? We already have a lot of these information, so why bother with an additional one? Well, I think some of the points on the slides are kind of self-evident. I mean, it's definitely like additional information that we can harness from the universe and can try and kind of see whether there are any deviations from what we see in the CMB, et cetera. And also, it's not only kind of the same, more or less, information, but it's actually also complementary information, and we can enhance the information that we can extract from the CMB. And then, in principle at least, there's much more statistical power in large-scale structure, because if we can go to kind of smaller and smaller scales, the number of modes that we're probing doesn't scale with kind of the multiple squared as in the CMB, because we're just measuring a surface, like a 2D surface. But in principle scales with kind of wave number cubed, because in principle we have both the angular positions on the sky as well as kind of redshift information, so kind of depth information. And in addition, there's, in principle at least, we can go to much smaller scales in large-scale structure than in the CMB. But that's obviously something where a lot of people in the community currently are working on in order to kind of make this actually happen. And if these points weren't enough for you, then you can just look at this, this list here of experiments that are operating or will be coming online very soon. I mean, DES already had their first data release. DESI has had first light, so they will be starting kind of taking science data sometime next year. LSST is obviously kind of up and coming, and then kind of the list goes on. Spherix is funded. Euclid will be flying. So we will have an enormous amount of data that we can kind of play with. But at the moment, at least, I think we're definitely not at a point where we say, well, that's everything that we can get out of the data, but there's still much more that we can learn from it. And so that's partly kind of what I'm motivated by, and what kind of this talk will tell you about. Some of these aspects this talk will tell you about. And so there's a whole kind of slew of possible observables that we can look at when we say we're observing the large-scale structure of the universe. Particularly, there's kind of weak lensing, with kind of DES being the prime experiment these days, or kind of Lyman alpha forest in galaxy clusters. But so what I'm focusing on kind of for the rest of the talk is essentially kind of galaxy clustering, meaning essentially that we're measuring the position of galaxies in the universe, and then kind of extract physics from that. And so the main observable in large-scale structure is, of course, the matter power spectrum, which is the Fourier transform of the two-point function of the position of galaxies, or in other words, kind of the two-point function of kind of overdensities in the universe. And it has this very characteristic shape with these essentially kind of two power laws here. The peak here is located at the scale of matter activation equality. And then on top of kind of these essentially kind of two power laws here, we have the kind of the small baryon acoustic oscillations that we all know and love from the CMB. And as is already depicted here, we battle with like one important, let's call it kind of systematic in large-scale structure, that we don't really face in the CMB. The CMB is mostly linear physics, but in the late universe, of course, due to the influence of gravity, the small perturbations that we have in the early universe grow and kind of at some point become nonlinear. And so we have to somehow try and kind of deal with that, these nonlinearities. And so that's great, but so there are these complications. And so what one can do is say, well, let's kind of split up this entire kind of spectrum here into kind of two parts. One part is the overall kind of broadband, kind of smooth shape here, which we call Pn no wiggle, NW. And then P wiggle here is kind of everything that kind of oscillates around this overall smooth shape. And this is what's known as kind of the baryon acoustic oscillation spectrum. And this is a plot taken from kind of BOSS DH12 data or kind of papers. And so it's showed these blue points are the data points. And you see, I mean, we have a very significant detection of the primal acoustic oscillations now in large-scale structure. And so, as I already said before, this is, of course, nothing else but the sound waves that are captured at the drag epoch just after recombination.
So you go back to the previous, so the x-axis is different from the left to the right. So
Yes, yeah. So I mean, so this here is a zoom in around kind of here.
I see. So it's a subset for a specific, it's not universal across the.
No, I mean, so I mean, the binary acoustic oscillations, as in the CMB, they are kind of on a certain scale, and in particular are silk damped. So if there was no such thing as silk damping, then kind of we would still see kind of the wiggles here. But due to kind of diffusion in the early universe, these peaks are damped, and hence kind of you can't see them here in the tail anymore.
So damping, right? This truncates the small size. What truncates
Yes.
the large size?
Well, I mean, so this signature is imprinted at a redshift of about 1,000. So kind of all scales, all modes that enter the horizon at later times don't have this feature. But I mean, so I mean, it kind of goes to 0 here, and then I mean, this is a log, of course, also a log scale and a linear scale. So yeah.
The data is different, right? So the bus data is much better and goes to 0.3, whereas when I made this plot, the distance data went into about.
Yeah. So an updated version of this plot shows many more data points, and also like the CMB data points here are kind of much smaller error bars and stuff.
Thank you for showing the old version of the plot that I made. It feels great, even though it's now out of date.
It's a great plot, so I really like showing it. In particular, with also the difference of the nonlinear versus the linear scales that we really have to kind of take into account. Okay, so that's the binary acoustic oscillations and the spectrums. And so it's clear that yes, we are throwing away information if you only look at the BAO spectrum. If you only look at the wiggles, we of course not taking into account information that's encoded in the broadband shape. But importantly, for kind of the purposes of the physics that I kind of will present in the rest of my talk, this actually doesn't matter. We don't have kind of information on these things in the broadband anyways, because these kind of the wiggles are still sensitive to the perturbations in the early universe. Like the overall shape, the broadband shape, that's essentially just coming about due to kind of the growth of structure in the late universe. Now, importantly, actually, this is one of the very neat things about the BAO spectrum. It's kind of less affected by these nonlinearities that I was mentioning earlier, and in particular, possibly even more importantly, we can actually analytically calculate their effects on the observables. So we can really get a good handle on what these gravitational nonlinearities are doing to the spectrum. And then, in addition, it has a number of additional perks, because we're taking the ratio of like the wiggle to the no wiggle spectrum. We essentially kind of dividing out a number of potential systematics that are at least getting kind of less important. And as I showed you earlier with the plot from BOSS, we now have both robust and high significance measurement of this observable. And so we can kind of readily use it with kind of public data that's available. And so with this long list of things and me telling you like how amazing this observable is, you might be asking, well, so for what has it been used so far? And that list is somewhat small. Essentially, not quite true, but essentially, this has been just used to extract the BAO scale, or currently the BAO kind of the frequency, and then using that as a kind of a standard ruler for the universe. But as I will show you now in the rest of my talk with two specific examples, there is much more information that we can harness beyond just kind of using it as a standard ruler and just extracting the BAO frequency. And kind of to be specific, first I will tell you about kind of a measurement that we did of the free streaming nature of neutrinos in the spectrum. And then in the second part, I will then move on from the early to the kind of very early universe and tell you about our feature search of the primordial spectrum in the same observable. All right, any questions so far? Okay, so let's talk about neutrinos. Kind of a short introduction to neutrinos in cosmology. The reason why we're so interested in studying neutrinos in cosmology is that on Earth, we have a really hard time measuring them because they are so weakly kind of interacting with the rest of matter. We need kind of huge experiments to just measure kind of a handful of these neutrinos. But in the early universe, they actually made up about 40% of the radiation density in the universe, with the rest being photons. Which means that during radiation domination, they make up 40% of the energy density of the universe, meaning they leave a sizable gravitational imprint, and hence we can kind of extract their imprints in the data, in particular in kind of the CMB, and as we'll show you also in colossal structure kind of today. And how this is usually parameterized is in terms of an effective, the effective number of relativistic species, which is normalized to be 3 if neutrinos were decoupling from the rest of the standard model in the early universe kind of instantaneously, and if there was no such thing as quantum electrodynamics, for instance, and a number of other effects. By considering neutrinos to not be instantaneous decoupling and including effects such as from QED, this number, the value of the standard model value of n effective is 3.04546, depending on the exact calculation. And so, yes. Now, as I already just said, neutrinos decouple at a temperature of about 1 MeV. So this means about 1 second after the Big Bang. And then essentially, because they're so light, essentially kind of travel at the speed of light ever since. Now, on the, kind of to the contrary, the photons are kind of strongly coupled to the baryons in the primordial plasma, and so they can only propagate information at the speed of sound, which is kind of c over square root of 3. So which is slower. Meaning that if you look at this cartoon version of the evolution of adiabatic perturbations in the early universe, which kind of start out here as kind of peaks, we see that kind of photons and baryons are kind of do the same thing, and they kind of propagate out at the speed of light, whereas kind of neutrinos are faster, so they're ahead of the sound horizon. And so if you kind of fast forward to kind of around kind of recombination, we see that a sizable fraction of the neutrino perturbations are actually ahead of the sound horizon. What this means is that there's obviously kind of quite a large kind of gravitational, they do have a gravitational potential associated to them, which means that neutrinos actually kind of slightly kind of drag, in some sense, the photons kind of ahead of the sound horizon. And so if one doesn't do this hand-wavy thing that I just did, but does the proper calculation, one finds that the fact that neutrinos are free streaming, they induce a phase shift to the photon perturbations, meaning that these are the acoustic peaks in the CMB. This is the CMB spectrum, just the damping, the overall damping removed. which means that what neutrinos do is they slightly shift all these peak locations coherently to larger scales. And so this is a very small effect. Yes?
Quick question. It's probably going to give away any understanding of this. In terms of it really, is it really just affecting the photons only as opposed to, say, the matter? Like baryonic matter, photons are a couple of this, but the baryonic matter is also having the tug from the dark matter, or is that not?
But essentially, kind of, at this epoch, we can kind of first kind of neglect kind of dark matter for these kind of effects. It's going to become important in a minute.
I guess my question is, why are the neutrinos only tugging on the photons?
I mean, as you see, so the dark matter perturbations also kind of grow this tail here, and that's because baryons and photons create this potential well that the dark matter is falling into.
We can chat more later.
Okay, sure.
Still
Okay, let's talk later. And so, okay, so what's important here is kind of this phase shift, in particular this constant phase shift here, is essentially only one of two ways that we can causally, so using kind of causal physics, can generate. So it's either kind of through free stream neutrinos, or if we had kind of isocurvature perturbations that are dynamically evolving in the universe. And so kind of focusing on neutrinos, as you can see here, it's a very small effect. If you kind of throw in kind of one more free stream neutrino, the shift here is just by kind of 5 multiples. So it's a very small effect, but we made a very important step with the Planck data, or the sensitivity of Planck, because now with Planck, we're not only sensitive to the background evolution of neutrinos, but we've actually measured the effect, this kind of phase shift effect in Planck data. And hence, this means that we are now also sensitive to neutrino perturbations. So we're sensitive to the neutrino perturbations on the photon perturbations.
So this effect relies on the assumption that acoustic perturbations propagate by sound. But if you have strong shocks, for example, strong shocks, then you see the speed of sound.
Sure.
So if this is the case, then it seems to me this effect would be much diminished.
But in that case, you would expect to see some additional signatures in the CMB, true. But as we showed, is kind of that the fact that you get a kind of a constant phase shift at large wave numbers, that seems to be pretty unique to anything that is kind of traveling faster than the sound horizon. And so in the sorry, say again. Sure, but so I mean, in a sense, if you just take kind of standard model physics into account, then it's kind of just neutrinos that can do that. Yes, I mean, if you have some other species or something else that is kind of propagating information faster than the sound speed, you could get an additional signature similar to this. Yes. Okay, so that's the CMB. Now let's go back to the evolution of our perturbations and kind of move the cosmological movie forward. At recombination, redshift of about 1,000 photons decouple, and so leave behind this kind of baryonic peak. And then what happens is the baryons fall into potential wells of the dark matter and vice versa. And so if you kind of move forward, kind of at late times, what you're left with is kind of a peak here at a radius of about 150 megaparsec, which is kind of which corresponds to the co-moving sound horizon. And so if we kind of, from this, what we expect is if we can look out into the universe, into the large scale structure, and measure the position of galaxies, we expect to find an excess of galaxy pairs that are 150 megaparsec apart. And so, well, this is exactly what we've seen with the BAO spectrum here. These oscillations here are nothing else but the Fourier transform of essentially kind of the square of this. Okay, so from that story that I've told you for kind of the phase shift in the CMB, and now kind of looking at this evolution of the perturbations, it probably doesn't come to a surprise to you if I'm telling you that we can theoretically see the same coherent shift of the peak locations also in the BAO spectrum of large-scale structure. And so this is exactly what this plot shows here. This is the kind of the BAO spectrum here. And again, if we increase the number of free streaming radiation in the universe, the peak locations coherently move to larger scales, or as shown here as a kind of an inset around here. And so now you might, however, say, well, so yes, this is kind of linear physics that's going on here to make this plot. But now you might say, well, but you told us that like nonlinearities are important and blah, blah, blah. So why should we ever look for this linear thing in large-scale structure? And here, it kind of becomes important that kind of Daniel Baumann, Dan Green, and Matthias Saldiaga a few years ago showed that actually kind of this phase shift here, particularly if it's constant, is actually immune to the effects of gravitational linearities, meaning that if there is a phase shift imprinted in the early universe, it remains the same, particularly also its magnitude remains the same at late times after the universe has undergone the nonlinear evolution. Which means, just turning that around, we can actually use kind of the linear prediction to search for this effect in nonlinear data. And so, hence, we kind of went ahead and kind of proposed to generalize the standard analysis of bioacoustic oscillations, which essentially are just kind of varying kind of one parameter, this parameter alpha, in some sense, just is varying kind of the sound horizon in the early universe. And so we said, well, so yes, we have the BAO frequency, but in order to, in addition to the frequency, let's also kind of measure the phase, which is parameterized by an amplitude and an overall template that is shown here. Because the phase shift is a constant at high wave numbers, but in the late universe, in particular during meta-domination, the effects of neutrinos, of course, gets smaller and smaller because their fraction of the overall energy density becomes smaller and smaller. And so it's no surprise that kind of the effect here kind of cuts off towards smaller wave numbers. And we take that effect into account.
So isn't this form degenerate? Because if you expand with a small beta, then you would just get higher orders in AK. So this is like
sure.
If you introduce this formula, there's a degeneracy between FK and AK. And you can choose different values.
Sure, but I mean, we know what f of k is supposed to be from our linear physics analysis. So we use exactly this shape. So if you look more closely, so these bars here are the measurement of the peak locations for 100 different cosmologies, kind of appropriately kind of rescaled. And so you see it matches pretty well. And so we know this kind of functional form here very well, and hence we can do that. Now, force shadowing, kind of something that you'll see in a little bit. Of course, also, as I just said, we want to measure both the frequency and the phase at the same time, but only with kind of a handful of peaks and troughs. So this means that we expect there to be quite a large degeneracy between kind of alpha and beta, or between the frequency and the phase measurement. Of course, like if we had an infinite number of kind of peaks and troughs available, yes, then we could kind of then there wouldn't be a degeneracy. but because we only have a finite amount of peaks, there will be one. And so with that, we got together with a few people from the Bosch collaboration and put this this proposal to work, and first tested this new pipeline extensively in forecasts as well as in mock catalogs. And then once we were satisfied, all the checks that we did went through, and so we then turned to the data, which was taken by the Sloan Digital Sky Survey and contains about 1.2 million galaxies, or redshift range of 0.2 to 0.75, which is binned in two redshift bins. And then in addition to the two parameters for the BAO frequency, we have 18 nuisance parameters that account for things like galaxy bias, uncertainties in the broadband shape, the damping scale, etc. And then in addition our phase shift parameter. And when we do that, this is the result. You see, so we here have the phase shift amplitude beta. Here we have alpha, the standard BAO frequency parameter. And then these two contours here are the two contours for the two redshift bins. And you see we have this huge degeneracy here. So, however, if we look at the underlying cosmology of a point here, so still in a 1 sigma contour, but far away from it, from alpha equals around 1, you will find if you look that up, if you compare that with the Planck results, it's way off. And so what we did in order to break this huge degeneracy here is something that has been done a lot in the CMB. So in the CMB, we make a measurement of our 6 lambda CDM parameters, and then in addition, put a prior on the sound horizon from the BAO. And so we just turn this entire thing around, and now do our measurement in large scale structure in the BAO, and put then a prior on the underlying cosmology from the CMB. In other words, we're saying that the cosmology, the underlying cosmology, should be consistent with Planck. And if you do that, we find these smaller contours here. And so the way beta is normalized is as follows. Beta equals 1 means it's what the phase shift that we expect in the standard model. Beta equals 0 means there's no phase shift, so there's no neutrinos are not free streaming. And so you can see here, we actually reject the hypothesis of no free streaming by more than 99% confidence. And of course, at the moment, the posterior is still pretty large. So this is certainly more of a proof of principle that we can extract additional data from the BAO spectrum. In this example on neutrinos and their free streaming nature. But in the future, as always, the future is bright. And so if you look at forecasts for the near and not so near future, we see that with DESI and Euclid, we'll be able to make this measurement more precise by a factor of 3 to 4. And in particular, if you compare the value that we can get from experiments such as Euclid, then we see that the sensitivity to the phase shift is more or less approximately the one that we currently have from Planck. So that analyzed separately, and then you might obviously imagine putting these two together and get a slightly stronger measurement.
Is this still with the CME prior?
Yes, this is still with the CME prior, but for experiments such as DESI and Euclid, the prior plays less and less of a role. I can show you a plot later where it's where it's just kind of large-scale structure. And in particular, if you imagine an experiment such as like this green curve, which might be kind of a spectroscopic follow-up to LSST or so, in that case, the CME prior doesn't really play much of a role anymore. All right. Are there any other questions regarding the neutrino part and their free streaming behavior for now?
How much are these bands affected if you have some modified dark energy W-1 or whatever?
I haven't done the analysis, but I would expect that it's kind of these kind of type of things are fairly insensitive to that, because I mean whatever you do with W is some kind of late time effect, and so we can pretty neatly distinguish that, I think. And the kind of the phase shift has like a very characteristic kind of shape and dependence, so I think we should be able to kind of distinguish them pretty well.
But I guess since you're dividing up the broadband, you don't recompute the broadband every time you change protocol.
No, I mean actually, so we throw away the entire information on the broadband, indeed, and so kind of W not WA or so would be contained there.
I guess the opposite is: are you biasing yourself away from those models because you're explicitly not sensitive to ones that are going to do some sort of either amplitude or some mild?
No, I mean, with this analysis, this analysis is kind of designed for the free streaming kind of the phase shift, and so if you're interested in doing like some W kind of physics, then you would kind of have to look more into it, and in particular, and then also like certainly the broadband shape carries much more information. And you would like to retain that, and here we just kind of literally threw it away.
Right, I guess what I'm saying is the word of caution would be if you were involved in the big BOS analysis, that you would take the best fit of their broadband and subtract that before you do yours, so that you don't. You can imagine getting two very different cosmologies, even if they included neutrinos in the broadband, because you're doing some CDM value and they're doing the best fit.
Sure. Yes. I mean, but so I mean, we marginalize over kind of quite a number of operant parameters. So I think essentially we should be completely insensitive to what the broadband is doing, even if it's doing something less.
But you marginalize over them by allowing them. How do you marginalize?
So I mean, so we have so just the standard kind of BOS kind of broadband shape, which is kind of modeled based on lambda CDM. But in addition, we then we kind of add kind of a polynomial with 6 terms and marginalize over all these effects. And so in particular, so this is kind of capturing nonlinearities and possible deviations of this model. And so and hence it should also as long as kind of this physics that you're introducing is kind of some smooth kind of physics, you're just kind of capturing that and kind of marginalizing that away.
Yeah, if you're doing that, then I'm not worried about any of this stuff.
So we're not fixing a broadband. We do have degrees of freedom to kind of account for variations. Okay. Yeah.
In the scale-dependent part that you calculate, what causes the small scale?
You mean these small kind of wiggles here? I mean, like, okay, so the curve here, that's certainly, well, that's just interpolated. So what you should look at is just kind of the dots themselves, or kind of these bars themselves. And there's certainly some kind of small scale kind of variations of like that affect kind of the overall kind of the peak locations. And so I haven't looked into detail of kind of what exactly is doing that, or what's generating that. But in particular for BOS kind of sensitivity, this kind of departure of this blue line to the red line don't matter like at all.
Do they come from specific realizations of the?
Yeah. So I mean, what I've done to generate this is I I sampled about 100 cosmologies with different values of n effective, and keeping a number of other kind of parameters fixed, and then kind of extracted the peak locations, and then appropriately rescaled them to account for, so basically appropriately kind of chose kind of beta that we have from kind of a theoretical model. Yeah, and so as these kind of error bars kind of indicate, they look very well. It's fitting kind of very well. And down here, we just ran into the problem that we're kind of close to metrization inequality, so kind of close to the overall peak. And so there's a disambiguity, or there's an ambiguity between kind of what belongs kind of to the peak of the broadband shape versus kind of the first peak in the BAO spectrum. Okay. So let's move on to, so that was the early universe. Now let's move on to the Primal Universe and look at features. But first to kind of set the stage in kind of standard, kind of vanilla, single field, slow roll inflation based on like a monomial potential. What we see, what kind of inflation predicts is kind of an almost invariant power spectrum. And if you look at the latest Planck data, one of the many things they do is they try and reconstruct the shape of the primordial power spectrum. And in the range of scales where kind of the CMB is more sensitive, we see that, yes, it looks approximately pretty kind of almost, or pretty kind of scale invariant, modulo kind of this kind of small spectral tilt. However, if you talk to an inflationary kind of phenomenologist or kind of model builder, then they will tell you that, well, I mean, you know, this is kind of great, but the phenomenology is kind of much, much richer. And so you know, almost generically, you would expect that you find like some kind of departure from this kind of this power law behavior.
Before you go on to that,
yes.
Can you remind the unwashed here what the constraints, existing constraints on MS are compared? Oh, that's the measured value.
That's the measured value of Planck 2018.
Okay.
Yes. So we have a very, very high significance measurement.
From the shape of potential, but it's not uniquely determined by single field slow roll.
No. Yeah.
You need to know more details about the potential.
Yeah. And so I mean, that's just the parameter. I mean, it's like you know this famous kind of NSR plot with kind of the monomial potentials and stuff. Models. So indeed. Okay. So we do expect from theory that the kind of inflation might not be as boring as just kind of one kind of scalar field rolling down kind of a monomial potential. But there's kind of more going on. In particular, if you turn to kind of some stringy realizations, then like you've got like much richer kind of structure than just kind of a smooth potential. And so some kind of broad kind of classes of kind of these departures here from kind of almost scalar invariance are called, for example, sharp features. So you can imagine that during inflation, you have some kind of particle production, or similarly, kind of your inflaton is kind of actually not kind of just rolling down, but actually kind of is having a sharp turn, or things like that. They give rise to kind of particular signatures. You might also have the case that actually you're not actually, the background evolution during inflation is not directly on the attractor solution, but just is oscillating around the attractor solution. That happens, for example, in kind of these models that are called axial monodromy. In that case, you get kind of so-called resonant features. And you can also have some kind of more general forms where you're talking about kind of standard clocks and they also give rise to kind of additional kind of features, additional kind of contributions, delta P here. And then, of course, I could kind of make this list kind of much longer, but these are some kind of generic classes, in particular of oscillatory behaving kind of contributions here. And so if you're now looking in particular at the phenology of sharp and resonant features, then what we usually find is the sharp features usually have some kind of linearly spaced kind of oscillations. And so kind of the form here looks very much similar to the form of the BAO. And the resonant features such as exon monodromy gives rise to kind of oscillations that are kind of equally spaced in log k instead of just a wave number k. And so, of course, if you look at kind of particular models, then you don't have only kind of this simple shape, but you might expect an additional envelope or some additional kind of running or kind of things like that. But these are kind of some generic kind of phenological kind of models that we can search for, and then possibly can map onto these kind of more complicated scenarios. You had a question?
Just a question about, if you go back a slide for the resonant features. I don't know a lot about inflation. Sort of my generic picture of resonance is that you have some sort of a driving oscillation where the frequency is matching some sort of a natural frequency. So is there some analogy of what those two, the driving frequency and what's driving it with the natural frequency for a non-cosmologist like me?
No, yeah, I mean, so you have this kind of this reoccurring kind of features, and so if we go to that plot, so this is kind of the red curves here. You see it's kind of equally spaced in log k, which is, I guess, kind of the more natural kind of way of kind of parameterizing things during inflation. So it's kind of recurring in kind of log k. So yeah, I think that essentially you can apply more or less your intuition that you have for resonances here as well. And so yes, and so kind of this is kind of what we kind of primarily essentially kind of looking at. We have kind of this almost scan power spectrum, which is shown here with the gray line, and then these kind of possible kind of oscillatory kind of behaviors kind of around it. And so in the CMB, this has been searched for ever since kind of WMAP data became available. And so there's kind of many different kinds of incarnations of kind of looking for deviations from this kind of power law behavior. There are kind of template searches, such as kind of the one similar to the one that we're going to be pursuing, but also kind of just reconstructions, such as kind of the first plot that I showed you, in kind of very different ways. People are trying to directly kind of reconstruct not only the primordial spectrum, but kind of the potential of the inflaton itself, and so on. And there are kind of a few kind of candidates with some marginal significance, but then, so it's kind of 2 sigma-ish. But then we are searching such a large kind of model space. For each model, we also search such a large kind of frequency range, like these omegas, that we kind of expect that, just that statistically speaking, there in a way have to be a number of kind of 2 sigma kind of deviations. Otherwise, you would live in a pretty peculiar place. But the upshot is essentially that there's certainly no significant detection, and the upper limits on the amplitude of these features is at the level of a few % relative to the kind of the overall scale amplitude. And just to give you kind of a range of scales, so the amplitude here is about 5% of the primordial amplitude. So kind of we're kind of around this level, a little bit smaller than that. And so as you expect, there to be kind of correlated signatures also in the bispectrum, because these features naturally produce non-Gauss entities as well. You can hope that by combining kind of the power spectrum and the bispectrum, that you can actually maybe kind of dig out something that's not quite significant in the power spectrum, but at least so far to no avail. So that's we are there at the moment.
How much freedom in the axiom monotony model is there in the amplitude of
from like theory, I think it's pretty kind of unconstrained. I mean, of course, it can't be like enormously large, but like there's definitely like the values that are viable from the data analysis are certainly fine. Yeah. Unfortunately, like, the theory priors aren't stronger than the data. Yeah.
So one of the sort of major attempts with the Planck data was to, stimulated by Viva, so we've seen in others, was to go away from those two specific forms.
Yes.
Allow for k-dependent, which of course then opens up a huge
Sure.
possible parameter space. But I don't know if LSS is ready for that. But have you thought about how that would work?
And maybe can come back to that question later, but in principle, as I kind of show you later, more or less like the techniques, in particular for like a template search that we have for the CMB, we can essentially kind of also apply to large scale structure after taking into account a couple of caveats. But in principle, we should be ready to kind of apply them. Okay, so kind of in large scale structure, this is how the metapower spectrum here at the top, or the correlation function, two-point correlation function at the bottom, get modified. And so, as you might expect, in particular here, the correlation function, if I put in a feature with a kind of frequency of 300 megaparsec, then similar to kind of the BAO here, we expect like an additional peak at 300 megaparsec. Now, for the log oscillations, the log frequency isn't like a particular physical scale, and hence because I mean, it arises not from like an event at kind of a particular time during inflation. So similarly, you find that you have like signals spread over kind of all kind of scales. But so kind of what's the kind of the status of kind of large scale structure searches for features? In essence, there hasn't been any analysis. A few people have kind of thrown in a few kind of large scale structure data points that come shipped with kind of COST-MC or Monty Python, and kind of when they did their CMB analysis, there have been kind of some kind of limited theoretical work on this and things that we might have to be kind of careful. But on the other hand, there have been kind of a whole kind of list of kind of forecasts for how well we can do in measuring features with experiments such as Euclid and LSST. Curiously, nobody has looked at what we can do now with kind of BOSS data. And so that's what we did and said, well, let's kind of look at it kind of more closely and try and kind of improve on kind of these points here, kind of step by step. And so the first step that we made was to say like, well, so we certainly don't need the entire metapower spectrum. It's fine to just look again at the wiggle part because well, these are primordial oscillations. They're certainly distinct from something smooth. So whatever kind of features we have in the metapower spectrum, they will be also just in the wiggle part here by definition. And so in particular, like the power law part of the power spectrum, that's divided out, and that's in the broadband shape. And so essentially what you're looking for is oscillations on top of the known binary acoustic oscillations. But unlike for the neutrino-induced phase shift, now we actually do have to kind of take the gravitational nonlinearities into account, as you might imagine, given that we have like a second peak in the correlation function. And this is kind of cartoon version, what kind of large-scale gravitational linearities do. Kind of in the late universe, we have kind of large-scale kind of bulk flows in the universe. And so what they do is they, on large scales, kind of move around kind of matter. And so if you imagined you had initially had like a perfect ring of particles, then due to these large-scale bulk flows, they kind of moved around and kind of end up being distorted. So if kind of the shape here of this ring was kind of the width was kind of was a Gaussian, then kind of at kind of later times this would be Gaussian with a kind of a wider width. And so this is what we certainly have to take into account when we do kind of standard kind of BAO analyses, because this kind of the peak in kind of linear theory is this this dashed line here. And so what nonlinearities do is they transfer power to kind of smaller and larger scales that can move them around in coupling modes, etc. And so kind of the peak is kind of less pronounced. And so this is certainly what we take into account in kind of standard BAO analysis. But given the plot that I showed you with this kind of distinct second peak at the feature frequency, we also have to do that for our features. And so you might wonder about the fact of like the small scale nonlinearities that are excluded for kind of the standard BAO, just because the BAO scale is so much larger. And so we can kind of do a similar analysis for kind of our features and kind of find it kind of similarly. As long as the feature frequency is large enough, we're fine. And so for the log features, I told you, well, they're scattered all over on all scales. But kind of what helps us is here is actually kind of the limitations of our experiments, because we're only sensitive in kind of a certain range of wave numbers. And so we can kind of take this certain range of wave numbers and essentially kind of expand these kind of logarithmic features into kind of a set of linear features. In some sense, we do like a kind of a Fourier expansion, and can then apply this argument to the logarithmic features and also find then kind of a lower value to which we can trust kind of our kind of linear theory prediction. Similarly, for kind of large-scale nonlinearities, there has been kind of extensive work for BAOs on how to kind of analytically extract and compute these effects. As I mentioned earlier, we can kind of compute that analytically. And so given that this shape for the linear features is essentially the same as for the BAO, we can use this same machinery and just slightly generalize kind of this formalism to kind of account for the fact that the frequency is not set at the sound horizon. And then for the logarithmic features, kind of this intuition that we have kind of for linear features breaks down, but the mathematical formalism still kind of go through. We can still kind of calculate along the same lines with kind of similar assumptions. And so what we find is similar to the BAO, also the peak due to the features is kind of exponentially damped, as kind of depicted here. So the standard kind of BAO part has this kind of standard kind of BAO damping, and the features in principle have a different damping scale, but it actually turns out that are pretty close. And for the level of kind of the Bose sensitivity, we can actually kind of just assume that this is the same. And so if we then look at the effects of these nonlinearities on our kind of predicted spectrum, we find that kind of there are kind of possibly kind of sizable kind of effects. And so if you want to get a reliable measurement and not completely overpredict our constraints, we do have to take this nonlinear damping into account. And so again, similar to kind of our work on the neutrinos, we again kind of validated this pipeline on kind of a whole slew of kind of forecasts and kind of mocks, and then kind of used the exact same data set as before, just with a kind of bunch of additional kind of parameters, and kind of restrict ourselves to this kind of frequency range, where the lower value is governed by the fact that we want to be safe from small-scale nonlinearities, and the upper limits are set by the size of the window function of the survey, or in other words, the caustic volume that we're probing. And so when you do that, that's the result. in kind of dashed and dotted are the two redshift bins kind of separately, and then in solid the combined results from large-scale structure BOSS data alone. And so, of course, the important question is now, well, how does this compare to the CMB? And that's shown on this plot here. And we see that we're very much competitive. And in fact, except around kind of a scale of about 150 megaparsec, so around kind of the BAO scale, where we, of course, have degeneracy of these features with the standard BAO. We are kind of very much competitive with Planck and actually able to slightly improve over Planck. Yeah, OK. So kind of in dotted here, it's just using the Planck temperature power spectrum. And then here, we have kind of Planck temperature plus polarization. So we use kind of the temperature auto spectrum, the polarization auto spectrum, and the cross spectrum. And so this is now just the standard analysis that's done by Planck. That's the baseline data set. And so, of course, what we can then do kind of in the very end is say, well, we have both kind of the CMB and large-scale structure. So just let's combine them and get the best possible constraints that we can have from current data. And that's kind of shown here. And of course, given the last plots, it's clear that kind of they are dominated by our results on large-scale from BOSS. And so just before concluding, we can kind of, again, look into the future. And again, the future is bright. At the moment, kind of the BOSS sensitivity is kind of around here. We have percent level measurements of the amplitude of these features. But then kind of going forward, kind of DESI Euclid will be able to kind of improve by half to kind of an order of magnitude. And then kind of going further into the future, kind of 2 orders of magnitude are certainly kind of in. And so this red line here might, for example, be something like kind of a pessimistic, small-scale version of an experiment called PUMA, which is currently being proposed as a stage 2 21-centimeter experiment. And comparing that with kind of the evolution in the CMB, we see that kind of even a acoustic variance-limited kind of CMB measurement over half the sky will kind of not be competitive with DESI over the range of scales, over the kind of the cosmic volume that we can probe with galaxy surveys. On for very large frequencies, the CMB will, of course, dominate, given the cosmic volume all the way back to recombination. And so to conclude, kind of a few kind of take-home messages that I want to kind of convey in this talk, or at the end of this talk. First of all, I mean, kind of there was going to be a lot of large-scale structure data, and so we should try and kind of be ready to kind of analyze it and kind of get the most out of it. And so I hope to have convinced you that even just kind of looking at a subset of all the possible observables or of the matter power spectrum can give us kind of very important pieces of information. And the 2 examples I showed were the neutrino-induced phase shift due to free streaming neutrinos and kind of constraints on these kind of feature models from inflation. And so before kind of taking more questions, I want to make a brief advertisement of a new initiative, which is called Cosmo Commons, which is trying to kind of bring kind of scientific discussions from the 20th century into the 21st century, and having an online platform to kind of discuss kind of recent papers, et cetera. So if you kind of want to know more about this, kind of talk to me or kind of look at this kind of tiny URL here. And similarly and independently, you can there's now also exists a Slack channel which is called Cosmic Discussion, which you can also which you're also invited to sign up to. If you have more questions, talk to me. Since I'm out of time, let's thank me for your attention.
was not understanding why that sequence of C and B curves of your last plot doesn't converge at at large omega ln, I guess. I mean,
Why?
limited by cosmic variance on large scales.
Well, so I mean, this essentially means that a feature with this frequency has such a small amplitude that you can't distinguish it given cosmic variance. Yeah.
Right, but how are you improving over Planck at very, very large scales?
No, I mean, so these features here, they are very highly oscillating.
But I see MPC here.
Yes, so this is slightly confusing. It's a frequency in Fourier space. So this means it's a location in correlation. So it's very it's at
-1 then, or whatever, or no?
No, it is a physical scale.
Yes.
So this means that the peak in the correlation function is at very large separations.
Okay.
And so if you kind of Fourier transform that, you find you have a very highly oscillating feature. And so actually kind of a omega ln of about 8,000 megaparsec corresponds to the Nyquist frequency of the caustic volume back to recombination.
So is this the Fourier transform of wave numbers, which is why it's...
Yes, so this is omega ln. You can think of it as kind of 2 pi over kind of the wave number of the feature oscillation. Yes.
I'm going to suggest we continue the discussion upstairs with cookies. So let's thank her.
Sounds good to me.